For most of human history, we assumed we were the center of everything. The stars were decorations, the planets were wanderers, and the universe existed, more or less, for us. Then science began dismantling that idea, piece by piece. First, we learned that Earth was not the center of the solar system. Then we learned our sun was not special, just one ordinary star among hundreds of billions in the Milky Way. Then we learned our galaxy was not unique, just one of an estimated 2 trillion galaxies scattered across the observable universe. At every step, the story moved in the same direction. We are smaller than we thought, less central than we assumed, more ordinary than we wanted to believe. And yet, after all of that humbling, one extraordinary possibility remained stubbornly on the table. Maybe, despite being cosmically insignificant in terms of size and location, we are profoundly significant in one other way. Maybe we are the only ones here. Maybe in all of this vastness, across all of this time, nothing else ever looked up and wondered. That possibility is what this documentary is about. And the science behind it, especially the discoveries made in the last few years, is more compelling than it has ever been. It started, as so many great scientific puzzles do, with a simple question asked at the wrong moment. The year was 1950. A group of physicists sat down for lunch at Los Alamos National Laboratory. Among them was Enrico Fermi, Nobel Prize winner, architect of the first nuclear reactor, one of the sharpest analytical minds of the 20th century. The conversation that afternoon had been light. Someone mentioned a newspaper cartoon about flying saucers. There were jokes, a few half-serious theories, the easy back and forth of brilliant people relaxing over a meal. Then Fermi went quiet. He looked around the table and asked, almost casually, "Where is everybody?" His colleagues knew immediately what he meant. The galaxy is ancient. It contains hundreds of billions of stars. Many of those stars are billions of years older than our own sun. If intelligent life had appeared on even a small fraction of the planets orbiting those stars, some of those civilizations would have had an enormous head start. Millions, possibly billions of years ahead of us. Enough time to develop technologies we cannot conceive of. Enough time to spread across the galaxy many times over. Enough time to leave evidence so obvious that even a young, primitive species like ours could not miss it. And yet, the sky was silent. No signals, no visitors, no ruins on any moon, no megastructures blocking starlight. Nothing. That question became known as the Fermi Paradox, and for over 70 years, it has been one of the deepest unsolved problems in all of science. Not because it is complicated to state, but because every honest attempt to answer it leads somewhere deeply uncomfortable. To understand why the silence is so strange, you need to understand why scientists expected noise in the first place. In 1961, astronomer Frank Drake scribbled a formula on a chalkboard at a small scientific gathering in West Virginia. He was not trying to calculate an exact answer. He was trying to organize a problem, to break a vast question into smaller, more manageable pieces. That formula became the Drake equation, and it remains one of the most famous mathematical expressions in science. The equation works by multiplying a series of probabilities together. How many stars form each year in the galaxy? How many have planets? How many of those planets sit in the right zone for liquid water? How often does life begin where conditions allow it? How often does that life become intelligent? How often does intelligence build technology? And how long do those civilizations survive? Each factor seems reasonable on its own. But when you multiply them together, even using cautious, conservative estimates, the result is striking. The equation consistently suggests that thousands of civilizations should exist in the Milky Way right now. Some estimates push into the tens of thousands. The galaxy, by this math, should be alive with signals and engineering and the accumulated evidence of countless minds that came before us. But it is not. It is quiet, completely, unnervingly quiet. For decades, researchers wrestled with that contradiction. They proposed explanations ranging from the logical to the terrifying. Maybe civilizations destroy themselves. Maybe they are hiding. Maybe they are sleeping. Maybe something hunts them. Each theory tried to bridge the gap between what the math predicted and what the sky actually showed. And then, slowly, a different kind of answer began to emerge. Not from the realm of speculation, but from hard data, from telescopes, from geological studies, from biology and planetary science and chemistry, from the actual evidence of how planets form, how life begins, and how extraordinarily specific the conditions for complex intelligence really are. That answer is the one this documentary is built around. And it does not involve predators or filters or civilizations that chose to go quiet. It suggests something far simpler and, in its own way, far more profound. We may be alone because the universe is not designed to produce minds easily. It is designed to produce rocks, oceans, bacteria perhaps in many places. But the chain of events that leads from chemistry to curiosity, from atoms to astronomers, may be so improbable, so dependent on a sequence of lucky accidents that it happened here and almost nowhere else. The rare Earth hypothesis, and the science behind it has never been stronger. Before we dig into that science, we need to spend a moment with the scale of what we are searching. Because the honest answer to the Fermi Paradox might simply be that we have barely looked. The Milky Way stretches 100,000 light-years from edge to edge. Inside that disk are between 200 and 400 billion stars. The total number of planets orbiting those stars is estimated to be in the trillions. And thanks to the Kepler Space Telescope and its successor TESS, we now know that planets are not rare at all. Nearly every star in the galaxy has at least one. The raw ingredients for worlds are essentially everywhere. Of those trillions of worlds, a significant fraction sit in what astronomers call the habitable zone, the band around a star where temperatures allow liquid water on a surface. Current estimates suggest there could be billions of such planets in our galaxy alone. Billions of potentially wet, warm worlds where, in principle, chemistry could get started. That sounds like a lot of chances for life, and it is. But here is where the story takes its first crucial turn. Having the right temperature is not enough. Having liquid water is not enough. Having carbon and nitrogen and phosphorus floating around in the right ratios is not enough. As it turns out, the list of conditions required to go from a habitable planet to an intelligent civilization is extraordinarily long, and the probability of any single world checking every box on that list may be vanishingly small. That is the core argument of the rare Earth hypothesis. And it was not invented by pessimists looking for reasons to feel lonely. It was built, piece by piece, from discoveries that kept pointing in the same direction. Every time scientists looked more carefully at what Earth actually required to produce us, the list of prerequisites got longer, and the odds got longer with it. We are going to walk through that list in the chapters ahead. Some of it will surprise you, some of it will unsettle you, and some of it, the part about what it all means for us, for our future, for what we do with this pale blue world we happen to find ourselves on, might just change how you see everything. But first, we need to sit with the silence for one more moment, because before we accept an answer, we owe it to the question to take it seriously. The most ambitious search for extraterrestrial signals ever conducted is the Breakthrough Listen project. Launched in 2015 with significant funding and access to some of the world's largest radio telescopes, it has monitored thousands of nearby stars across a wide range of frequencies, looking for any pattern that might suggest an artificial origin. So far, nothing confirmed has been found. One astronomer described the scope of our search with an analogy that is difficult to shake. Imagine the entire search space, all the stars, all the frequencies, all the possible directions and timescales, as the volume of Earth's oceans, every drop of water in every ocean and sea on the planet. Our search so far amounts to roughly the contents of a hot tub, maybe a small swimming pool if you are being generous. We have not searched the ocean. We have barely dipped a finger in. That is a legitimate caution. The silence might reflect our limitations more than reality. And we should hold that possibility honestly, without dismissing it. But here is what makes the rare earth argument different from a simple shrug. It does not rely on the absence of a signal. It relies on the presence of data, specific, detailed, testable scientific findings about what Earth required to produce intelligent life, and how unlikely that combination of factors appears to be when you examine it carefully. The silence in this framework is not the main evidence, it is the confirmation. The main evidence is written in the rocks beneath our feet, the chemistry of our atmosphere, the peculiar orbit of our moon, and the geological accident that gave this planet its beating heart. That evidence is what the next chapter is about. And once you see it laid out in full, the question will no longer be why the sky is silent. The question will be how, against every odd the universe set against us, we ended up here at all. Here is a question worth sitting with before we go any further. What does it actually take to build a planet capable of producing intelligent life? Not just life. Bacteria can survive in conditions that would kill anything we recognize as complex. But intelligent life, the kind that develops language, builds tools, discovers mathematics, and eventually points telescopes at the sky and wonders if anyone else is out there. For most of the 20th century, scientists assumed the answer was relatively simple. You need a rocky planet. You need liquid water. You need to be the right distance from your star. Check those 3 boxes and you are in business. Life would follow, intelligence would emerge, and the galaxy would fill up with civilizations the way a tide fills a harbor. Naturally, inevitably, given enough time. That assumption turned out to be wrong. Not slightly wrong, profoundly, fundamentally wrong. The more carefully scientists examined what Earth actually required, not just to host life, but to produce minds capable of asking questions about the cosmos, the longer the list of prerequisites became. And the longer the list grew, the more it started to look like Earth was not a typical outcome of planetary formation. It started to look like an accident, a long, improbable, almost unrepeatable accident. That is the heart of the rare Earth hypothesis, and the evidence for it comes not from pessimism or guesswork, but from geology, astronomy, biology, and planetary science. Hard disciplines with hard data pointing consistently in the same direction. Let us walk through it, step by step, condition by condition. Because only when you see the full picture does the weight of it truly land. Start with location. Not just the location of Earth within our solar system, but the location of our entire solar system within the Milky Way. The galaxy is not a uniform place. It has structure, a dense, chaotic core packed with stars so close together that radiation levels are lethal to any complex chemistry. It has spiral arms where star formation is active and supernova explosions are common enough to periodically sterilize nearby worlds. And it has a thin, relatively quiet ring between those extremes, far enough from the dangerous center, rich enough in heavy elements to build rocky planets, and calm enough to allow billions of years of stable development. Scientists call this the galactic habitable zone, and our solar system sits squarely inside it. That might sound like a given. Of course, we are in a habitable region, otherwise we would not be here to notice. But the point is not that we are here. The point is how narrow that zone is relative to the total volume of the galaxy, and how many star systems fall outside it. The majority of stars in the Milky Way are either too close to the dangerous core or too far out in the sparse, element-poor outer regions to support the kind of planetary chemistry that complex life requires. We are in the right neighborhood. That is the first item on the list, and the list is long. Next, consider the star itself. Our Sun is a G-type main sequence star, stable, long-lived, and relatively calm. It has been burning at a consistent temperature for roughly 4.5 billion years, and it will continue doing so for several billion more. That kind of long-term stability matters enormously for life. Evolution is slow. Building complexity from scratch takes time, billions of years of it. A star that varies wildly in output, or that flares violently and regularly, does not give life the stable runway it needs. The most common stars in the galaxy are red dwarfs, smaller, cooler, and far more numerous than stars like our Sun. They make up roughly 70% of all stars in the Milky Way. For a long time, they seemed like promising candidates for hosting life, precisely because they are so common. But the more we have studied them, the more problems have emerged. Planets in the habitable zones of red dwarfs orbit so close to their star that they become tidally locked. One face permanently baking in starlight, the other frozen in permanent darkness. The temperature difference between those two hemispheres creates violent atmospheric circulation that may make stable surface conditions nearly impossible. Red dwarfs also tend to be highly active in their youth, blasting nearby planets with intense ultraviolet and X-ray radiation during the very period when life would be trying to get started. Some researchers believe life could still survive in the narrow twilight band between the hot and cold sides of a tidally locked world. That is possible, but it is a far cry from the broad, stable, temperate conditions that allowed complex life to flourish across most of Earth's surface for hundreds of millions of years. Our Sun, by contrast, gave us stability, consistent light, manageable radiation, a steady hand over an enormous stretch of time. That is rarer than it sounds. Now, we come to the piece of the puzzle that surprised even the scientists who discovered its importance. Plate tectonics. It sounds like a dry geological topic, the kind of thing you half remember from a school textbook. But plate tectonics may be one of the single most important ingredients for intelligent life in the entire universe, and almost no planet we have studied appears to have it. Earth's outer shell is not one solid piece. It is fractured into massive slabs that float on a layer of semi-molten rock below, grinding past each other, diving beneath one another, and occasionally crashing together to push up mountain ranges. This slow, constant movement drives one of the most important cycles on the planet, the carbon cycle. Here is how it works. Volcanoes along plate boundaries release carbon dioxide into the atmosphere, which warms the planet. Over time, rain pulls that carbon out of the air and washes it into the ocean, where it eventually sinks into the crust. When tectonic plates slide beneath each other in a process called subduction, that carbon gets pulled back into the mantle, where heat and pressure eventually send it back up through volcanoes. The cycle repeats continuously over millions of years. This loop acts as a planetary thermostat. When Earth cools, volcanic activity releases more carbon and warms it back up. When it heats, weathering pulls more carbon down and cools it. Without this system, Earth would have frozen solid billions of years ago, or cooked itself into a Venus-like furnace. Either way, complex life would have had no chance. Now look at every other rocky planet in our solar system. Mars had volcanic activity once, but its interior cooled and solidified billions of years ago. Its tectonic system died. Its atmosphere was stripped away. Today, it is a frozen desert with no meaningful protection from radiation. Venus may have had tectonics early in its history, but something went catastrophically wrong. Its surface appears to have been completely resurfaced by massive volcanic events, leaving behind a thick toxic atmosphere and surface temperatures hot enough to melt lead. Mercury has no tectonic activity at all. Earth stands alone, the only rocky world in our solar system where plates actively move, recycle, and regulate the climate across geological time. And the reason it has this system traces back to a single violent event, one that almost certainly did not need to happen, and probably does not happen on most planets. Roughly 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact was catastrophic on a scale that strains imagination. Rock vaporized. Oceans that had not yet formed were replaced by a global magma sea. The debris ejected into orbit by the collision gradually coalesced into what we now call the Moon. And the energy delivered deep into Earth's interior by that collision reheated the planet's core, delivered extra radioactive elements that still generate heat today, and, according to a growing body of research, may have directly triggered the plate tectonic system that has regulated our climate ever since. A 2025 study reinforced this connection, arguing that the Theia impact provided the earliest evidence of subduction, the key process that drives plate tectonics, within just a few 100 million years of the collision itself. Without that impact, the evidence suggests Earth might have ended up with a solid dead shell like every other rocky world we know. No recycling, no thermostat, no stable climate over billions of years, no US. The collision was not inevitable. It was not written into the laws of physics that a Mars-sized object would strike a young Earth at exactly the right angle and velocity to produce the specific outcomes it did. It happened. And because it happened, a chain of consequences followed that eventually led to complex life, intelligence, and this documentary. But the moon was not just a byproduct of that impact. It turned out to be something Earth needed in its own right. Our moon is unusually large relative to the size of Earth. No other rocky planet in our solar system has a moon anywhere near this proportionally massive. And that size matters in a way that took scientists decades to fully appreciate. The moon's gravitational pull stabilizes the tilt of Earth's rotational axis. Without that stabilization, our axial tilt, currently around 23 degrees, which gives us our seasons, would wander chaotically over time, shifting between nearly 0 degrees and potentially over 80 degrees. The climate consequences of that wandering would be extreme. Ice ages would come and go with brutal unpredictability. Seasons would shift beyond anything life as we know it could reliably adapt to. With the moon holding our tilt steady, Earth's climate has remained relatively predictable over hundreds of millions of years. Not perfectly stable, ice ages still came and went, but stable enough for complex ecosystems to develop, diversify, and eventually produce intelligence. Remove the moon, and that stability goes away. Remove the stability, and the evolutionary path that produced us becomes far less likely, possibly impossible. And then there is Jupiter. The largest planet in our solar system sits far out in the cold reaches beyond the asteroid belt, and its enormous gravitational field has been quietly protecting Earth for billions of years. By capturing or deflecting asteroids and comets that would otherwise cross Earth's path, Jupiter significantly reduces the frequency of catastrophic impacts on our planet. Without Jupiter acting as a gravitational shield, the rate of large impacts on Earth would be dramatically higher. Life would be periodically reset before it had time to build complexity. The long, uninterrupted stretches of stability that allowed evolution to produce animals, then vertebrates, then mammals, then primates, then us. Those stretches might never have existed. Stack all of this together, the right position in the galaxy, the right type of star, a planet in the habitable zone with a strong magnetic field, active plate tectonics born from a catastrophic collision, a large stabilizing moon produced by that same collision, a gas giant acting as a distant shield, billions of years of relative calm, liquid water on the surface maintained by a functioning carbon cycle. Each condition on its own might be achievable, but needing all of them simultaneously on the same world across the same era, that is a different calculation entirely. It is like rolling a dozen dice and needing every single one to land on 6. Any one of them landing differently and the chain breaks. And the chain breaking anywhere means we are not here. This is what separates the rare Earth hypothesis from simple pessimism. It is not saying life is impossible elsewhere. It may well exist. Simple life, microbial life, chemistry in the ocean life, on many worlds scattered across the galaxy. The universe is large enough and old enough that even extraordinarily improbable events happen somewhere. But intelligent life, the kind that builds civilizations, develops technology, and reaches out across space, requires something more than a warm, wet rock. It requires a precise and unlikely alignment of planetary, stellar, galactic, and geological factors that may have come together in our favor almost entirely by chance. A 2024 study published in Scientific Reports attempted to quantify this more rigorously. When researchers factored in the rarity of plate tectonics, the specific ratio of ocean to continent required for complex ecosystems, and the narrow range of stellar types that provide the right kind of long-term stability, Their estimate of genuinely habitable worlds in the Milky Way dropped by several orders of magnitude compared to earlier, more optimistic models. Not billions of Earth-like worlds, perhaps thousands, perhaps far fewer, perhaps at the level required to produce intelligence, just one that we know of. The universe did not make us easily. It made us reluctantly through a sequence of accidents that did not have to go the way they did. And understanding that changes the way this story ends, not with fear, but with something closer to responsibility. Because if we are rare, then what we do with this rare thing matters more than we have ever fully reckoned with. That reckoning is what the next chapter is about. We have established that Earth sits in the right place, the right galaxy, the right position within that galaxy, the right kind of star, the right size planet, with the right geological system keeping its climate stable across billions of years. That is already an extraordinary run of good fortune. But here's the thing. All of that only gets you a habitable planet. It does not get you us. It does not get you a species capable of language, mathematics, philosophy, or space travel. The gap between a warm, wet rock with a functioning carbon cycle and a civilization pointing radio telescopes at the stars is enormous. And filling that gap required its own separate sequence of accidents. Biological this time, not geological, each one just as unlikely as the last. This chapter is about that sequence, the chain of evolutionary events that had to happen in roughly the right order, at roughly the right time, to produce intelligence on Earth. And what becomes clear when you lay it all out is that the chain did not have to connect. At multiple points, it almost did not. And if it had broken anywhere along the way, we would not be here to examine it. Start with oxygen. For the first 2 billion years of life on Earth, the atmosphere contained almost none of it. The planet was dominated by methane and carbon dioxide. Life existed, simple, single-celled, anaerobic life. But it breathed nothing like what we breathe today. Then, around 2.4 billion years ago, something changed. A group of microorganisms called cyanobacteria began producing oxygen as a byproduct of photosynthesis, releasing it into the atmosphere in quantities that had never existed before. The result was one of the greatest catastrophes in the history of life on this planet. Oxygen is chemically aggressive. For the anaerobic organisms that dominated Earth at the time, it was poison. The Great Oxidation Event, as scientists call it, killed the vast majority of living things on Earth. It was a mass extinction driven not by an asteroid or a volcanic winter, but by the waste product of a microbe. But for the life that survived and adapted, oxygen opened a door that had been closed since the beginning. Aerobic metabolism, using oxygen to release energy from food, is dramatically more efficient than the anaerobic alternative. It unlocked the energy budget needed to build larger, more complex organisms. Without the Great Oxidation Event, the path to animals, to vertebrates, to mammals, to us, is almost certainly closed. The cyanobacteria did not evolve to save the future. They were just doing what microbes do, but the timing and the scale of what they produced changed everything that followed. Then came the event we touched on in the previous chapter, but it deserves a closer look here because its biological implications are staggering. Around 1.5 billion years ago, one cell engulfed another. Under normal circumstances, the engulfed cell would have been digested, but something went differently. The inner cell survived. It persisted inside its host, and over generations, the two became inseparable. A single organism with a division of labor that had never existed before. The inner cell, stripped down over millions of years of coevolution, became the mitochondrion, the power plant of every complex cell on Earth today. This event, endosymbiosis, is considered by many biologists to be the single most important transition in the history of life after its origin. It is what separates simple prokaryotic cells from the complex eukaryotic cells that make up every animal, plant, and fungus that has ever existed. Without it, life on Earth would almost certainly still be microbial. The entire kingdom of complex organisms, every creature that has ever moved, hunted, grown, or thought, traces its existence back to that one improbable merger. And here is what makes it genuinely remarkable as a data point. As far as scientists can determine, it happened once, in 4 billion years of life on Earth, with countless trillions of cells engulfing other cells in countless environments across the entire planet. That particular merger, the one that stuck, the one that worked, the one that led to complexity, appears to have occurred a single time. Once, in 4 billion years. If that is not a filter, if that is not the kind of event that almost never happens, it is difficult to imagine what would qualify. Fast forward to the animal kingdom. Life has now been complex for several 100 million years. The oceans are full of creatures. Evolution is running its endless experiments. And then, 66 million years ago, a rock roughly 10 kilometers across hits what is now the Yucatan Peninsula in Mexico at a speed of roughly 20 kilometers per second. The impact releases energy equivalent to billions of nuclear weapons. The sky fills with debris. Sunlight is blocked for months, possibly years. Temperatures plunge. Photosynthesis collapses. The food chain disintegrates from the bottom up. Roughly 3/4 of all species on Earth go extinct, including every non-avian dinosaur that had dominated the planet for over 160 million years. From one angle, this is pure catastrophe, and it was. But from another angle, the angle that matters for our story, it was the opening of a door. For most of the Mesozoic era, mammals existed. They had been around for over 150 million years alongside the dinosaurs, but they were small, mostly nocturnal, living in the margins of a world dominated by reptiles far larger and more powerful than anything the mammals could compete with in open daylight. Evolution had given mammals intelligence, warm blood, and adaptability. But the ecological space to use those advantages was largely blocked. The asteroid removed the blockade overnight. In the aftermath of the extinction, mammals diversified explosively into the ecological niches left empty by the dinosaurs. Over the next tens of millions of years, they grew larger, more varied, more specialized. Primates emerged. Then apes. Then, around 6 million years ago, the lineage that would eventually produce our genus split from the lineage that produced chimpanzees. And here is the point that the rare earth argument rests on. That asteroid did not have to hit. There was nothing inevitable about it. The solar system is full of rocks on various trajectories, and the overwhelming majority of them never come anywhere near Earth. The one that ended the Cretaceous period arrived by chance, at a specific angle, at a specific location, at a specific moment in the history of life that happened to be exactly when mammals needed the opportunity most. Remove that asteroid, and the dinosaurs likely continue. Mammals likely remain small and marginal. The primate line, our line, either never develops or develops into something unrecognizable. Intelligence of our particular kind almost certainly does not emerge. We owe our existence in part to a rock that had no intention of helping us. But even after all of that, the oxygen revolution, the cellular merger, the asteroid, the rise of primates, intelligence was still not guaranteed. The evolutionary path from early primate to modern human required its own series of developments, each one contingent on the ones before it. Bipedalism freed our hands. Freed hands allowed tool use. Tool use drove the development of more sophisticated cognition. More sophisticated cognition enabled language. Language allowed the transmission of knowledge across generations. The accumulation of culture, the foundation of civilization. Each step built on the last, and each step could have gone differently. Other species have pieces of this. Dolphins are intelligent. Crows use tools. Elephants demonstrate empathy and memory. Chimpanzees have rudimentary culture. But none of them combined all of these traits in the specific configuration that allowed one species to go from stone tools to space telescopes in a few 100,000 years. That configuration, upright posture, precise hands, large prefrontal cortex, complex vocal anatomy, and a social structure that rewarded cooperation and communication, came together in our lineage and, as far as we know, nowhere else on Earth in 4 billion years of trying. The universe ran the biological experiment on this planet for 4 billion years. It produced intelligence once, one species, one time, after billions of years of opportunity. That is not the output of a process that runs easily or reliably. That is the output of a process that almost never works. And occasionally, in the right conditions, under the right pressures, with the right sequence of accidents, somehow does. There is one more piece of this biological argument that tends to get overlooked, and it connects directly to the Fermi Paradox in a way that is easy to miss. Consider ocean worlds. Current planetary models suggest that a large proportion of rocky planets in habitable zones across the galaxy may be water worlds. Planets entirely covered by deep global oceans, with no dry land, no continents, no coastlines. Some estimates suggest water worlds could actually outnumber Earth-like planets with exposed land by a significant margin. Now consider what intelligence requires. Beyond just biology, it requires technology, and technology requires something that ocean worlds cannot provide: fire, metallurgy, agriculture, construction. Every foundational step of technological civilization depends on dry land. You cannot smelt metal underwater. You cannot build a radio telescope on the ocean floor. You cannot discover fire in the deep. Dolphins are intelligent. They have been intelligent in various forms for millions of years. They will never build a civilization. Not because they lack the raw cognitive capacity, but because their environment does not allow the next step. Intelligence without land is intelligence with nowhere to go. The galaxy may be full of ocean worlds teeming with complex, even intelligent life, creatures that think and feel and communicate in ways we would recognize as sophisticated. And every single one of them will remain permanently silent, not because they were destroyed or because they chose to hide, but simply because they have no way to reach beyond the water. Earth had land. It had the right ratio of ocean to continent, enough water to sustain life, enough dry surface to build upon. That ratio is not guaranteed. It depends on the total water delivered during planetary formation, the size of the core, the geological activity that pushes land above sea level. Get any of those slightly wrong in either direction, and you end up with a desert planet or a water world. Both are dead ends for technological civilization. We threaded that needle too. Another item on a list that keeps growing. By this point in the argument, the rare Earth hypothesis is no longer a philosophical position. It is a scientific one, supported by a growing body of evidence from multiple independent disciplines. Every time researchers look more carefully at what Earth required, geologically, astronomically, biologically, the picture that emerges is the same. We are not a typical outcome, we are an outlier. A product of a specific, unlikely, non-repeating sequence of events that happen to unfold on one planet around one star in one corner of one galaxy. That does not mean we are certainly alone. The universe is vast enough that even extraordinarily improbable events can happen more than once. But it does mean the Fermi Paradox may not be a paradox at all. The silence may not require a dramatic explanation. No predators, no filters, no civilizations choosing to hide. The silence may simply be the natural result of intelligence being genuinely, profoundly rare. And if that is true, if we are among the first, or perhaps the only ones, then the next question is the most important one our species has ever faced. What do we do with that? For most of the history of the Fermi Paradox, the debate lived largely in the realm of theory. Smart people making educated guesses, equations filled with variables we could not measure, probabilities built on assumptions rather than data. The Drake equation, for all its elegance, was essentially an organized list of things we did not know. That is changing. Fast. In the last 5 years, a wave of new scientific discoveries has begun replacing guesswork with actual evidence. Telescopes powerful enough to analyze the atmospheres of planets orbiting distant stars. Geological studies rewriting our understanding of what made Earth unique. Biological research revealing just how contingent the path to intelligence really was. The data is coming in, and it is painting a picture that looks increasingly consistent with one conclusion. Complex, intelligent life is extraordinarily rare, possibly unique to Earth. And the universe, for all its staggering size, may have produced minds in only the most exceptional circumstances. Here is what the newest science is actually showing us. The James Webb Space Telescope has been operating for just a few years, and it has already forced scientists to revise some of their most optimistic assumptions about life beyond Earth. In 2023, Webb made headlines when it detected carbon dioxide and methane in the atmosphere of a planet called K2-18b, a world roughly 8 times the mass of Earth, orbiting in the habitable zone of a red dwarf star about 120 light-years away. Some researchers suggested the chemical combination could be consistent with an ocean beneath a hydrogen-rich atmosphere. There was cautious excitement. A few headlines went further than the science warranted, but the follow-up analysis told a more complicated story. K2-18b orbits a red dwarf, the kind of active flaring star that bombards nearby planets with radiation during exactly the period when life would need stability to get started. Its size puts it in a category called a sub-Neptune, which likely means a thick hydrogen atmosphere sitting above a high-pressure ocean with no rocky surface beneath. The conditions bear almost no resemblance to early Earth. The chemicals Webb detected have plausible non-biological explanations that researchers are still working through. The finding was genuinely interesting science, but it was not evidence of life, and more importantly, it illustrated something crucial. Finding a planet in a habitable zone with interesting chemistry is not the same as finding a planet capable of producing intelligent life. The gap between those two things, as the rare Earth hypothesis argues, is enormous. Meanwhile, updated habitability models published in 2024 have significantly narrowed the estimate of truly Earth-like worlds in the galaxy. When researchers applied stricter criteria, factoring in not just temperature and liquid water, but the specific requirements of plate tectonics, long-term stellar stability, protective magnetic fields, and the right continental-to-ocean ratio, the numbers dropped sharply. Earlier models suggested billions of potentially habitable worlds in the Milky Way. The newer, more rigorous estimates suggest the number of worlds capable of producing complex life may be orders of magnitude smaller, thousands perhaps, hundreds in more conservative readings. That shift matters. It means the silence of the sky is becoming less surprising with every refinement of our models. The universe is not withholding something common. It may simply not be producing it very often. The newest research on plate tectonics has sharpened this further. A 2025 study confirmed that the Theia impact, the collision that formed our moon, left detectable signatures in Earth's mantle chemistry that directly link that ancient event to the onset of subduction, the engine of plate tectonics. The implication is significant. Plate tectonics on Earth was not an inevitable consequence of planetary formation. It was triggered by a specific catastrophic accident that left a fingerprint we can still read today. No other rocky planet we have studied shows comparable evidence of that kind of impact-driven tectonic initiation, which means the geological system that has regulated Earth's climate for billions of years, the system without which complex life almost certainly could not have survived, may owe its existence entirely to one violent collision that did not have to happen. The universe gave us an extraordinary gift, and it gave it to us by accident. What all of this adds up to is a picture that would have seemed almost defeatist to the optimistic astrobiologists of the 1990s, but that now looks increasingly like where the evidence is pointing. The Fermi Paradox may not need a dramatic solution. No predators, no filters ahead of us, no civilizations choosing silence. The answer may be simpler, quieter, and in its own way more profound. We do not hear anyone because there is almost no one to hear. Not because the universe is hostile to life, but because the specific chain of events required to go from chemistry to curiosity is so long, so contingent, and so dependent on accidents that almost no planet ever completes it. We did. Somehow, improbably, against the odds that the universe set against us at every turn, we did. And that changes everything about what comes next. We have covered a lot of ground. We started with a question asked over lunch by a physicist who could not make the numbers add up. We walked through the scale of the galaxy, the depth of the silence, and the decades of searching that have found nothing confirmed. We examined the chain of geological accidents that made Earth habitable, the right star, the right position, the catastrophic collision that built our moon and started our tectonic system. We traced the biological lottery that produced complex life, then intelligence, then us. And we looked at what the newest science is saying, that with every refinement of our models, the estimate of worlds capable of producing minds like ours keeps shrinking. All of that leads here, to the question that the science cannot answer on its own, but that the science makes unavoidable. If we are rare, possibly unique, what does that mean for how we live? Let us be precise about what the rare Earth hypothesis is actually claiming. It is not saying the universe is lifeless. Simple life, microbial, resilient, chemically creative, may exist in many places. Oceans beneath the ice of distant moons, warm subsurface pockets on otherwise barren worlds. Chemistry doing what chemistry does when water and energy are present. But intelligent life, technological life, the kind that builds and questions and reaches, that may be something the universe has produced only here, on this one small world, in this one brief window of cosmic time. If that is true, then we are not just another species on another planet in an unremarkable corner of the galaxy. We are, as far as anyone or anything knows, the only way the universe has ever looked at itself and understood what it was seeing. The only mirror the cosmos has ever held up to its own face. That is not a comfortable thought. It is a heavy one. But it is also, if you sit with it long enough, a genuinely extraordinary one. There is a version of this conclusion that leads to despair. If we are alone, some people feel the universe becomes a colder, emptier place. All that space, all that time, and nothing out there to share it with. The silence stops being a mystery and becomes simply the truth. And the truth, in this case, is lonely. But there is another version, and it is the one worth holding on to. If we are rare, then we are also irreplaceable. Every piece of knowledge we have gathered, every work of art ever created, every moment of genuine human connection, every discovery that pushed our understanding forward, none of it exists anywhere else. It is not being duplicated across 1,000 civilizations on 1,000 worlds. It is here, only here. And if it disappears permanently, with no backup, no second chance, no other version of the story playing out somewhere across the stars. That changes the stakes of everything we do, not in a paralyzing way, in a clarifying one. The rare Earth hypothesis, taken seriously, is one of the most powerful arguments for the long-term survival of our civilization that science has ever produced. Not because it tells us we are special in a flattering sense, but because it tells us we are responsible in a way that nothing else could. Every risk we take with this planet, with our climate, our weapons, our capacity for conflict, our relationship with the technologies we are building, carries a weight that extends far beyond our own generation. If we are the only minds in the galaxy, then the extinction of humanity is not just a tragedy for us. It is the permanent silencing of the only voice the universe has ever found to speak with. The cosmos spent 13 billion years and an extraordinary run of unlikely accidents producing something capable of understanding it. We are that something, and what we do with the next 100 years, the next 1,000, will determine whether that 13 billion year investment meant anything at all. The search for extraterrestrial intelligence is not over. It should not be over. The James Webb Space Telescope is still scanning distant atmospheres. The square-kilometer array will soon listen with more sensitivity than anything we have built before. The Habitable Worlds Observatory is being designed specifically to image Earth-like planets and look for the chemical signatures of biology. We should keep looking. We should look harder, across more frequencies, with better instruments for longer periods, with more imagination about what a signal might look like. The rare Earth hypothesis is the most compelling answer the evidence currently supports. But science does not deal in certainties. It deals in the best explanation available until a better one arrives. If something out there answers back, we update everything. Immediately, completely and gratefully. But if the silence continues, if the next generation of telescopes sweeps the sky with unprecedented power and still finds nothing, then the hypothesis will not feel like defeat. It will feel like confirmation of something that was always quietly implied by the data: that we are alone, that we matter, that what we do here matters more than we have ever truly allowed ourselves to believe. Enrico Fermi asked where everybody was. He asked it simply, between bites of food, in the middle of an ordinary afternoon. And the question has echoed through science ever since, growing heavier with every passing decade of silence. Maybe the answer was never about them at all. Maybe the answer was always about us, about what it means to be here, against every odd the universe placed against us. About what we owe to the accidents that built us, and to the future that is still, against all probability, ours to shape. The galaxy is silent, and we are the reason it is not completely dark. What we do next is everything.